Hello, in the last two lectures we got an overview of compliant mechanisms and also discussed what it means to have the spirit of compliant design in order to take advantage of various features that compliant mechanisms possess. Today we look at the very important aspect, which is applications. Whenever you do something different or something new, people naturally ask what is the application. Today's lecture is focused on applications of compliant mechanisms. So, let us look at first the question, what are the applications? I would say that the answer for this is rather moot, in the sense that whatever rigid body mechanisms can do, compliant mechanisms can do that also, right. In other words, whatever applications that rigid body mechanisms or rather conventional mechanisms have, compliant mechanisms also are amenable for all those applications. In that sense, asking specifically what are the applications of compliant mechanisms, as I said, is in a sense a moot point. You should not even ask that. But when you are learning about compliant for the first time, naturally you would want to know what the applications are. First thing that I would say is that there are lot of applications in consumer products, and I will show some of them now. So, you might have seen the shampoo bottle lids, which are bistable. So, you can have this one, this is not really shampoo bottle, some bottle, it is I think intensive care Vaseline, it does not matter. Many plastic bottles today have these lids which are bistable. So, they go either that position or this position, and there is another snap fit here which kind of closes it tightly, and there are different versions. Here is another one which is really Head and Shoulders shampoo bottle, which has this bistable, very well pronounced. In fact, it makes noise when I switch from one state to this is one state, open state, and that is the closed state. Okay. There are these bistable devices, a number of them, and here is another one of the same kind in a different color. Now, this is I think Kissan ketchup bottle lid, that also is bistable. So, there they have very interesting what I would call a three-dimensional compliant mechanism, what is sometimes called a butterfly hinge, which has very thin shells which have this bistable behavior. And we had already seen an example of the brew jar, which actually closes the lid very tightly, and here another one which probably in India is not so familiar. It is a floss pick, it is a dental toothpick come a device with which you can do flossing, that is between teeth. So, this has a very interesting behavior, that there is this segment which is very slack at the beginning. The moment I press it here, it becomes taut. It becomes taut, so you can put between teeth and clean. So, there are a number of these consumer products that exist in the market, and these are all applications. How they are designed, we have no idea, because that is usually not published in the literature, technical or scientific literature, but these products are there. If we come back to the list of applications that we have on the slides, there are also lot of accessories in machinery and appliances. There are a lot of compliant mechanisms there. Here is one real application where Professor Larry Howell at Brigham Young University has applied it to put it into a lawn mower. Lawn mower, if you think of it as an appliance or a device, and here is where the compliant mechanism is. It is an overrunning clutch. The white one that you see is the overrunning clutch. That basically, depending on the speed, the clutch will engage or not engage. So, that kind of a thing you can have with plastic or with metal as well, what you see at the top. Okay, that is a real application. Another one that one of my undergraduates had done a long time ago is the bicycle one-way clutch. If you ride a bicycle, if you ride forward, pedal forward, you go forward, right, and if you try to pedal backwards, then you stay put, meaning that at that time the torque from the pedals is not transferred to the chain that moves your wheels. So, it is a one-way clutch, only one direction it transmits, other direction it does not transmit. If you take apart one of those, where I have the chain sprocket wheel still visible here. There will be many parts. Instead of that, you can have basically two compliant pieces. There is a red color, underneath that there is a blue color, and that basically has like a compliant pawl or ratchet, which will make it go only in one way and not the other way in terms of transmitting the torque. So, they are all real applications that one can use in appliances and devices. Here is one more, that what we see on the right side is what is called a tweel from Michelin. Tweel is tire plus wheel. So, tire plus wheel is a portmanteau word which becomes tweel. So, Michelin had experimented with this concept. We do not see it in use now. When I say it is a tubeless tire, it is basically tire itself acts like a tube or whatever functional the tube, a pneumatic tube does. As you can see in this picture, this one looks like a flat tire, but actually it is not. It basically has a compliance in all around this hub, which takes all the shocks and acts like a springer and a damper, but it is an interesting concept of compliant design. Looking at this, some years ago, one of my master's students, Bhargav, did this for a bicycle. Of course, as you can see here, the spokes or whatever have been replaced with compliant segments. Here we retain the spokes, because when we try to imitate this, it was becoming as expensive as the bicycle itself. So, Bhargav came up with a concept of putting something in any tire of any size in any bicycle. There is no tube at all. There are tubeless tires, but they are still pneumatic, but here it is non-pneumatic. You just have one hoop in it, which acts like a pneumatic tube to take all the shocks, even though just like Michelin wheel, it looks like a flat tire, but it provides you the good ride that one wishes in a bicycle, and it can be retrofitted on a tire of any size and any bike, any bicycle. So, it is also a real application. And moving on to another application, let us look at precision mechanisms. Precision mechanisms have used compliant design or compliant mechanisms long before this field took this name. The reason for that is very clear. When you want precision in a mechanism, in a machinery, you want very precise motion. That is, if you want it to move by 2.3 millimeters, it has to move by 2.3 millimeters, not a micron more, not a micron less. If you use rigid body linkages, it will be very difficult to do, because they have friction and they also have backlash, which we had discussed in the first lecture. So, friction and backlash are not problems that are associated with compliant mechanisms. They do not have, because there are no rubbing parts and there is no lag time for engaging something. Only when you have joints and there are two surfaces which have to contact for the motion to ensue. In compliant mechanisms, when you use a fully compliant mechanism, meaning the one that does not have any kinematic joints at all, any kinematic pairs, then it is void of the problem due to friction and backlash. So, people have been using in precision mechanisms. Here is an example. This is an XY stage which has lot of these beams. Each beam is actually a representation or a compliant version of a sliding joint. We talked about sliding pairs, elastic pairs in the first lecture, and here is one of those. They are arranged in a particular way, 8 of them, 1, 2, 3, 4, 5, 6, 7, 8 around this XY stage. It has 2 degrees of freedom. We will talk about degrees of freedom a little later. You have 2 motors, 2 actuators to move this in XY directions, and it is really precise. If you use a good motor, which normally people use what is called a voice coil motor, then you can have very precise, almost nanometric precision you can get with this, because it is a compliant mechanism. And there is another version of this, again it looks very complicated, but just like the previous one, which decouples x and y motions, here also it does decouple x and y motions. In addition, there is a block here which is basically a displacement amplifying compliant mechanism, which you see here, Of course, there are two layers. There is if you want to put in a single layer, the previous one had 8 blocks. Let us go back and look at it. As already counted 1, 2, 3 in the top row, and then 2 in the middle, and then 3 in the bottom row. These things are arranged. If you look at this one, if this is upright, this is upright, this is upright, this is upright. So, 1, 2, 3, 4 are upright, and these are 90 degrees turned, 1, 2, 3, half of them. When you arrange them in this particular configuration, you decouple the x, y degrees of freedom, even though it is all made of one piece. Now, if you want to amplify the motion of the actuator, whatever it moves, you want a longer range for the stage, then you need to have a different configuration, which is the one that is shown here. You have the central stage, and then there are 12 building blocks, each of them identical. They have a DACM and a compliant suspension. This particular thing shows a sliding joint and a displace amplifying compliant mechanism. When you arrange them in this particular fashion, 12 of them, you get this, or you can arrange them 6 in each plane and attach at the stage, you can get this mechanism. This also will be suitable for precision motion along with enhanced range. So, there are application precision machinery, a lot of them are there. Like I said, these were in existence even before compliant mechanisms field took shape in late 1980s and early 1990s. Now, let us move on to another very interesting application, which is micro nano systems. At the very small scales, assembly is a big problem. It is not like you cannot do it, but if you do it, the advantage of microsystems, especially what is known as micro electromechanical systems field, there if you have a process that involves assembly, the cost of the device is going to be very high. And in fact, MEMS are inexpensive, mainly because on a single wafer you can make a number of devices without having to assemble part by part. The moment you have something that has joints, even though fabrication processes do allow fabrication of joints without actually assembly, but the process becomes expensive. Once again, people do not want that, because MEMS, like electronics, have to be really cheap. So, using compliant mechanisms makes a lot of sense, and that is what people have been doing without even thinking. It is like very natural for using compliant mechanisms in micro and nano scales devices and systems. Here is one such device that one of my former PhD students, Samudha Khan, had done, which is what is shown here is a packaged micro machined accelerometer for 2 axes. I am showing this because it uses exactly the stage that I just showed in the precision mechanism application. So, we have the proof mass here. Moving the mass is not the one, rather acceleration will cause the mass to move. You can measure the displacement using, let us say, capacitance. Here you see a lot of capacitance comb fingers over here. Instead of that, if you put a DACM, that is, we have that thing here. Here is the proof mass, here is all that arrangement of 12 building blocks that I talked about in a single plane, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, if it is horizontal, this is vertical, this is horizontal, and then we have this a version of the DACM, and this is going to give you a lot more displacement of the sensing comb fingers as opposed to the displacement of the proof mass. And it is all done, you can see the silicon scanning electron micrograph here, and the width of these beams is typically 5 microns, or as small as the fabrication process allows. And the compliant mechanism beams also you see here very tiny, and there is no assembly involved. So, you can have complicated mechanisms, compliant mechanisms made using photolithography. Here is a single axis accelerometer shown, that was a 2 axis here, here is a single axis and corresponding scanning electron micrograph here, which again you can see compliant with some nicely made here. It just looks like the graphical computer graphics image that you see there, and it is a 2 axis one. The chip that goes in this part, it is magnified and showed here, this is a packaged one. When you do this, you get, I put this thing called improved. What does it improve? Here it improves both resolution or sensitivity as well as the bandwidth. Bandwidth meaning for what frequency range this accelerometer is going to work as it is intended, and here usually in accelerometers there will be a trade off between sensitivity and resolution and bandwidth, because sensitivity is m over k is proportional to mass divided by the spring constant, whereas resonance frequency, which is related to bandwidth, is k over m. So, they have trade off between, if you achieve one you have to compromise the other, but when we use this compliant mechanism DACM here, you do not have to make that compromise, it really gives you an improved thing. And here again the crucial one is the compliant mechanism. Suspensions are one and DACM is another. And looking at another sensor, it is not really micro small, although it can be made micro small as well, it is mesoscale. You see the device here is if you look at the dimension here, it will be about centimeter size. Okay. So, this particular width from here to here is 6 millimeters. If this middle one is 6 millimeter, let me draw it. So, this thing here is 6 millimeters, you can imagine the other one will be couple of centimeters this way or that way. Here you have a probe, this is the probe, and if you apply a force here, that is if there is a force that comes like this, there will be amplified motion here, there will be amplified motion here, which can be picked up with a digital microscope. Digital microscopes are quite inexpensive these days, and that digital microscope looks at this. You can do image processing and get with this device a resolution of 2 micronewtons. Okay. Look at the size of the device, it is in centimeters, but you can actually resolve 2 micronewtons over a range of about 1 millinewton. And you see this aluminum casing, and the mechanism can be just inserted like a cartridge, and it has this capability of measuring micronewton, which is quite uncommon in commercial devices, because there are excellent force sensors up to about millinewton or 0.1 millinewton, and then much lower nanonewton, femtonewtons. There are a lot of advanced force microscopy techniques that are available, but in between there is neglected region, and mechanisms here fill that gap. And here is a small movie that let me just play that. So, you can see what this has. It just shows a 1 minute video of how this micronewton force sensor based on a compliant mechanism works. This was done in our lab, and my student Gautam is actually showing that it does not have anything other than a compliant mechanism and this digital microscope over here that looks at it, and of course, it comes with a USB drive, and you connect to the computer, it does connect it to a program which gives you the ability, as we will show experiment. If you take a feather and touch it, you do not feel a force, that micronewton force our fingers cannot feel, but this sensor was tested to show that when you have these after feathers which are called downy barbs, when you touch them and move with this probe that are attached to the compliant mechanism, that shows in this image you can see it is moving ever so little, which shows the mechanism given reading, which gives you how much force there is. Moving on to another application, which is smart material based systems. Many of the smart materials are so called active materials, especially let us say piezoelectric one. It can give you a lot of force when the stroke is small. In fact, most of the piezoelectric materials when they are stacks or otherwise, compared to the force that they can deliver, the displacement is quite limited. So, you need a mechanism to convert that large force and small displacement to large displacement against some smaller load. And one such application that we had worked on, a number of people have worked on using compliant mechanisms for piezoelectric materials, electrorestrictive materials and shape memory alloy materials and a number of others. The idea here is, let us say I want a device to be operated with piezoelectric actuation, which gives very small displacement of the order of let us say a few microns, and there will be enough force that you can use that force, as you can see in the compliant with the middle figure here. This movement you hardly see, whereas here you see what was there has moved from there to here. Okay. It is able to retract when apply the force here. There is also inversions, that is, we look at what is happening here. Let me draw this. So, here is where the piezoelectric is pushing and it is coming down, but quite a lot if you see, right. It can amplify displacement. So, this is one version that was made with metal. Again I emphasize, any material can be used for making compliant mechanisms. Here it was done with aluminum or spring steel, where you can apply piezoelectric actuation there, and this moves almost by a millimeter by taking a 25 micron stroke of the piezoelectric actuator. So, smart material based devices need compliant mechanisms as transmissions. In automotive like cars, you have engine and then transmission, and then you have the tires or wheels where it turns the wheels. So, here also between actuator and the load, which will be on this side. So, this is the loading side, and this is the loading, and this is the actuation. In between you have what we can call transmission. So, this thing is transmission. So, compliant mechanisms can act like transmissions for smart material based devices. There are a number of applications related to this, and Professor Mary Frecker at Penn State University has pursued this angle quite a bit in her work. Let us look at aerospace applications. Again, there are a number of applications. In each category I am showing only one or two examples just to tell you what are the application areas. Aerospace, one of the very interesting applications that we had mentioned probably in the first lecture as well, is to have this adaptive compliant wings, what are called shape morphing wings, because the aerofoil shape is optimal aerofoil shape is going to be different in different conditions of the aircraft. Let us say while taking off or cruising, landing, there will be different airfoils, and normally people use these flaps, right. There are hinges basically. Instead of that, you can have something as it is shown over here. It naturally just curves this way or that way and gives you the right profile everywhere, not just the flaps here, the entire shape of the airfoil can be changed. It is a big application because even a small change in the shape can affect overall efficiency, fuel efficiency of the aircraft, because small changes in this particular case create a very large effect on the overall lift and drag on the aircraft wings, and these are really huge devices, these compliant mechanisms. What you see here is an aircraft where the normal wings are not adaptive or compliant wings, but the compliant wing is actually over here. This is for the testing purpose, this is only for testing while flowing, but now these have been moved to the real wings, that is from being underneath. After all the wind tunnel tests, instead of doing this, you can do it right here by putting these devices, and these are applications also in windmill blades. Depending on the wind conditions or direction of the wind, you can change the airfoil so that you gain a lot from the power generated. So, there are really interesting applications, shape morphing, there are many other things in aerospace components. Here is a version of that. There is a company called Flexsys, I think it is Flexsys. You can look at that website to see how this compliant wing changes its airfoil shape as per the need. When you give an actuation inside, wings are actually there is not that much room there in the towards, especially towards the tip, but there is where you need the deformation, and that can be done with compliant wings that are inside this. Moving on to another area, which is biomedical. There are lots and lots of applications here. Let us say surgical tools. There are a number of applications where you want to again avoid joints in things that go inside the body, because if you have that, if you have joints in between, there could be lot of bacteria, virus, everything can get stuck. Sterilization becomes a problem. If you do not have joints, sterilization becomes easy, nothing gets stuck because there are no small narrow spaces for things to get stuck. So, biomedical devices have lot of applications in surgical tools and lot of biosensors as well. There are also actuators. Here is an example of a valve replacement compliant device. If there is a defective valve in the heart such as here, you want to insert a new valve and put it in place, and that can be done. In fact, a company has adopted this technology, EndoValve. You can look at the company website. The name might have changed now, but still if you go to that EndoValve, they redirect you to a new company which is still marketing this. So, this particular one I will show a small video of that. You can see how a compliant mechanism can be used to deploy a valve which is tucked inside a catheter. So, it has to be a very small tube that goes into the heart to replace that. Okay. So, into that the compliant which is completely tucked in into this tube, it will be inserted. Once it goes into the heart, you deploy like an umbrella and then place it. What the doctor with whom we had worked had said was Dr. Herman Howard. He said that sometimes they place it and they want to take it back if it is not positioned right. So, it had to have 3 states of completely closed in like this and then opened, it puts there, and then it goes into state where you can actually place it and change it back if you want, if it is not positioned properly. In this video you only see that being placed, you can see the compliant mechanism, all these beams that are bending, right. So, that is the beauty of compliant mechanisms, where you can make tiny devices that have complex functionality such as this one. Biomedical devices, there are many more applications than what I am presenting now. Here is one for tissue cutting. So, there are 2 needles, let me get the pen. There are 2 needles here, there is one over there, another one whose tip you do not see, 2 needles in this position. It is a planar mechanism, basically needles are over there. Okay. And you have one actuator here that goes back and forth. It is a stepper here, it can be any actuator. When this goes back and forth, these tips here will trace a complex path like this, and this one goes like that. There are 2 paths, let me change the color for the second one. There is one path, other path goes like this and this way. There are 2 paths like this here. So, how are they achieving this? Even though the input here is smooth, the output that you see that these things will undergo is non-smooth, meaning they have a non-differentiable point. There is a cusp, it comes like this and suddenly changes direction and goes back like that. So, over here there is this cusp that changes direction. That happens because there is contact happening here and here. So, let us watch a video, a movie for this, and all we are doing is moving this back and forth. Oh sorry, I should not have touched it. So, let us play this video. Okay. So, you have these 2 things moving, and here it is only going back and forth. The moment contact happens here and here as well as here, that is where it changes the direction of the path. By repeatedly doing this, if there were to be a cell or tissue, you can cut it out. So, you can do it very fast. Of course, this is intentionally played very slow. If you do it fast, it will cut in the same place repeatedly. If you put sharp needles, it can tease the tissue out. So, you can say this is the tissue I want to cut, it can just take it out in the laboratory applications or even real surgery. So, you can get complex motion out of compliant mechanisms, and you can even suture with these things. And here is another application in the biomedical area where I have to get the arrow now. Yeah. So, a biological cell, here it is a MCF7 breast cancer cell, which will only be 10 microns or 12 microns in diameter, and that is being grasped with a compliant mechanism, which you see when it comes into focus, you can actually see it being slightly squeezed while this tube is looking on. That tube is only to position it, it is a pipette with which you can push and pull and position it there. But the idea is that you can do mechanical characterization of biological cells. And the automotive applications are too many that I am not even showing. There are a lot of little parts in the cars and motorbikes and the trucks and other things, so or even railways. There are a lot of little devices which can use compliant mechanisms. I will show something in the area of robotics, again showing one of our works where we had designed an external pipe crawling device, where there are a bundle of pipes, you imagine, and the thickness of each pipe has to be monitored. The pipes are so close that you have to have a very compact device that crawls on the outside of the pipes, not inside. Inside, let us say, has corrosive fluid and you want to monitor the thickness of the pipes, it has to ride on the pipes. This is one of those that was designed with shape memory alloy actuation. In that, what was interesting was there was a circumferential input that causes the radial output for this to hug the pipe or release, and so it can go like monkey. There are two rings here. When this is holding, this is free, it can move, and then once this becomes tight, this loosens and this spring will bring it back like inchworm motion, like a monkey would climb a tree, a coconut tree, and that is how this works. And this used the active material, smart material, shape memory alloy, and very compact compliant mechanism made of spring steel. So, in robotics there are a lot of other applications, or transmission. Here is an example where you have an actuator with certain characteristic. It could be hydraulic or pneumatic, in which case it will be just flat with respect to the stroke, whereas electrostatic, piezoelectric, all these actuations or active or smart actuations would deliver less force as the stroke increases. But if you want to get hydraulic pneumatic type, you can use compliant mechanism as a transmission and try to get something like a flat response, that is, force will be constant irrespective of the stroke, and you can use mechanisms such as this. That is another application. There are many more applications of compliant mechanisms, and you can look up the slides. There is no need to explain all of that. Here you can have micromechanical signal processors, you can use band pass filtering, switches, relays, frequency translators, even clocks using compliant mechanisms. Just to recap, our application areas are very vast, and we only looked at one or two examples from each application area, and there are many more application areas. Again, one thing to remember is that whatever rigid body linkages or conventional mechanisms can do, compliant mechanisms can also do that job. Thank you.